One of the really good examples of where this anti-periplanar geometry plays a role can be seen in this particular example. So, let me take an example here, and I am going to start with a cyclohexane derivative. In this case, I am going to start with this methyl bromocyclohexane, right, and we are going to react it with, let us say, methoxide for the E2 type of reaction. Now, when the elimination reaction is going to happen, remember that the leaving group and the hydrogen, the beta hydrogen, has to go anti-periplanar. Now, if we were to ask what is the more substituted product of this particular reaction, the answer would be this, right, because it results into the formation of a more substituted carbon-carbon double bond. However, what we observe is that the major product of the reaction comes from this particular product. So, how is this possible? Why is the more substituted carbon-carbon double bond not formed, or why is the Zaitsev's rule not obeyed in this case? Okay. What we are going to do is, first, in order for us to do this reaction, remember that we need to make the hydrogen, the beta hydrogen and the leaving group go opposite to each other, or in the anti-periplanar geometry with respect to each other. In order to do that, what we are going to do is, okay, we are going to first convert it to the corresponding chair. Okay. So, let us draw the chair. We know that, let us put the bromine going up, and then 1 and 2 on the second carbon, the methyl should go down. Okay. So, that is how the chair is going to look like. Okay. Now, for the elimination to happen, for it to go anti-periplanar, what are the possible hydrogens that are anti-periplanar to this particular bromine? As you can see, when we draw the chair, the methyl group on carbon number 2 is really anti-periplanar to that bromine, and that is kind of counterproductive because it does not help us to eliminate the beta hydrogen from that carbon, right. In fact, the beta hydrogen here on carbon number 6 is anti-periplanar to it, it is going in the opposite direction. Just to illustrate the point, we are going to look at this model here. This is the bromine going up, and the group anti-periplanar to it is actually the methyl that is going down. So, this does not help because what I need is a hydrogen that is going opposite to it. Remember that if the chair flips and if the axial goes to equatorial, that also does not help because in this case the bromine does not have anything anti-periplanar to it, right. When the bromine goes equatorial, there is no group anti-periplanar to it. So, the bromine can be only eliminated, or elimination reaction can happen when the bromine is in the axial position, okay, and that axial position is like this, right. Now, on this carbon you do not have any hydrogen that goes anti-periplanar, but on this carbon, the carbon number 6, you have a hydrogen that goes in the opposite direction as compared to that bromine, and as a result of which the elimination product will come when we eliminate from carbon number 6 here, okay. And that is the reason why the Zaitsev's rule is not followed here. Although in principle any base can do an E2 reaction if we change the reaction conditions, more often it is seen that good bases are good at doing E2 kind of chemistry. So, when we want to employ bases to do elimination reactions, chemists choose bases that are really strong. They will use bases like hydroxides, they will use bases like alkoxides, amide anions, compounds like LDA, which is lithium diisopropyl amine, or compounds like tertiary butyl lithium, which is one of the strongest base that you will see. These are the bases that are used to do E2 kind of reactions. If you see the characteristics of all of these bases have conjugate acids with the pKs that are above 11. Okay, so if you see the pK of alkoxide, for example, alkoxide like ethoxide will have its conjugate acid as ethanol, and this ethanol has a pK of 16, right, or hydroxide, which has a conjugate acid as water, and water has a pK close to 16, right. So, good bases are the compounds that have conjugate acids with pKs above 11, okay. And whenever we want the elimination reactions to favor, we use bases that have pKs of their conjugate acids above 11. When we are using bases with the corresponding conjugate acids with the pKs below or near 11, more often they can do substitution reactions as well. So, compounds like carboxylates, compounds like thiolates, cyanides, azides, or compounds like really good nucleophiles like bromides, chlorides, they all have their corresponding conjugate acids to have pKs below 11, okay. Thus, chemists need to choose the kind of nucleophiles or the kind of base they want to employ to do a particular type of chemistry. We just looked at an example where the Zaitsev rule was not followed, and we formed a less substituted alkene because the right kind of geometry in the transition state could not be achieved, right. And we are going to look at one more example where the Zaitsev rule is typically not followed, and that is when we are using a really bulky base, okay. And that happens for really bulky bases like tertiary butoxides. Sometimes it is also seen for compounds like LDA, okay. So, tertiary butoxide is basically a compound which results when you deprotonate tertiary butanol, right. So, for example, here I have a sodium tertiary butoxide molecule, okay. As you can see, this particular molecule tertiary butoxide is quite bulky, it is a big molecule because it has that tertiary butyl group at one end of it. Now, when this molecule wants to attack on the starting material that I have shown here, remember there are two types of beta hydrogens. Now, since this is the alpha carbon, couple of beta hydrogens are present here, and this particular hydrogen is also a beta hydrogen. So, I have kind of shown all the beta hydrogens in blue. What is seen is when compounds like tertiary butoxide react, they want to approach the beta hydrogen, but because of their size, because of the bulkiness of the base, it cannot reach that particular proton effectively. In turn, what it prefers to do then is to grab a proton from the less substituted carbon where there is lesser steric hindrance, okay. So, what we see is when these kind of reactions take place, it results into the formation of this as the major product, whereas the more substituted alkene is seen as a minor product, okay. And this is one of the case when the less substituted alkene is preferred. Now, if I take the same compound and if I react it with a smaller base like a sodium methoxide, this base would prefer picking up that proton from the more substituted carbon, and it would result into exactly opposite ratio, and we would form this as the major product and this as the minor product. So, one thing to pay attention to is also what kind of base we are using. Typically, really bulky bases prefer to form the less substituted product to avoid steric hindrance. Okay, so we have seen now 4 types of reactions. One is SN1, SN2, then E1 and E2. And we have said that SN1 and E1 kind of compete with each other, right, because both of them go through a carbocation formation, and once the carbocation is formed, either it can result into an elimination product or it can result into a substitution product. Similarly, since both SN2 and E2 both require strong base or correspondingly strong nucleophiles, what you can see is that they compete with each other too, and you will get a product that comes out of SN2 or E2 or a product ratio in a particular reaction. and more often it can be really confusing to determine which one of these two processes will dominate or what kind of reaction will happen given a particular alkyl halide and a particular nucleophile or a base, right. It could be confusing to come up with the product. So, what I am going to do is we are going to walk through the step by step process to determine which products will arise from which reactions. Okay. So, now let us begin our discussions with the methyl alkyl halides. Now, methyl alkyl halides are compounds like CH3X, right, or CH3Br, CH3Cl, CH3I, right, and these are compounds which are very easy to predict because they will never undergo an elimination reaction because there is no beta carbon, there is also no beta hydrogen present, right. So, they will never undergo elimination reactions. For methyl alkyl halides, SN2 is typically a favored reaction because it is favored with good nucleophiles and it will proceed in a polar protic or polar aprotic solvent, but typically polar aprotic solvent is preferred for SN2 reaction. Okay. SN1 reactions for methyl alkyl halides are very rarely seen because it involves the formation of a primary carbocation which is really not stable. We do not see an SN1 reaction happening on a methyl alkyl halide. So, more often methyl alkyl halides have only one fate, that they can undergo SN2 type of reactions. Okay. Now, let us talk about primary alkyl halides, and after primary the thing gets a little complicated, right. Let us talk about primary alkyl halides. Now, for primary alkyl halides, compounds like ethyl, propyl, 1-butyl bromide, when the leaving group is attached to the primary carbon. Okay. Now, primary alkyl halides are going to do SN2 when they are put in with good nucleophiles. Okay. Good nucleophiles but weak bases like azides, like cyanides, like bromides, like thiolates, and all of these will be good nucleophiles for an SN2 reaction, and this will prefer a polar aprotic solvent over a polar protic solvent. But however, it is not like the polar protic solvents will not do the reaction. The reaction will happen, but it will just prefer or will happen better, will happen faster in a polar aprotic solvent. Primary alkyl halides also do E2 type of reactions, and E2 will happen in a really strong base, okay, and also a bulky base, okay. And SN1 and E1 typically on a primary center, since they both involve carbocation formations, are not seen. So, we do not see carbocation formation on the primary carbon very effectively. So, SN1 and E1 are also not allowed for primary alkyl halides. So, if I have to think about primary alkyl halides doing reactions, the first thing I ask is a nucleophile or a base really strong, right. So, these include bases like tertiary butoxide, NaNH2, LDA, butyl lithium, really strong bases. Then more often, rather than substitution, these strong bases want to do elimination because it is more basic than more nucleophilic, and so it will form elimination products. Okay. If the answer is no, and if you have really good nucleophiles, so as I said, compounds like cyanides, azides, bromides, iodides, even some of the really good smaller bases like hydroxides, alkoxides, if all of these are the condition, as you can see, then the substitution reactions, SN2 reaction is preferred. Okay. Although SN2 is the major product, you also see a minor product resulting from elimination reactions from compounds that are really good bases as well. So, for alkoxides and hydroxides, for example, you will see a minor component coming from the elimination reaction as well. Okay. That is one case. If that is still not the case, and if you have a really weak nucleophile like water, like ethanol, methanol, compounds like ammonia or acetic acid, all of these are really weak nucleophiles, and if that is the case, then the substitution will happen, but it will happen very slow with the help of SN2 type of reaction. Again, it will be a slow reaction because SN2 requires a really good nucleophile. Okay. So, the final thing that can do is substitution via SN2. So, that is the fate of primary alkyl halides. Okay. Now, let us come to the more tough part, which are the secondary alkyl halides. Now, why they are tough is because they are kind of in between. For the primary alkyl halides, as we had seen, you cannot form a carbocation very effectively. So, SN1 and E1 kind of do not happen for primary alkyl halides. Whereas, for the tertiary alkyl halides, as you will see, SN2 does not happen very effectively because there is a lot of steric hindrance. But secondary alkyl halides are kind of in between, and they are, I call it as a mushy zone. It can do both SN1, SN2, E1, E2, all sorts of reactions depending on the kind of nucleophile that you are using. So, let us go over the secondary alkyl halides in detail. Okay, so, for SN2 reactions, remember that the secondary alkyl halide is little more hindered than primary alkyl halide, and therefore, it prefers doing elimination a little more than substitution. Okay. However, it is not like substitution does not happen, substitution will happen, but there is a little more preference given to the elimination of the secondary alkyl halide. Okay. So, when we are using really good nucleophiles such as bromides, cyanides, azides, but not really good bases. So, all of these compounds are great nucleophiles, they are not great bases. So, a rule of thumb that we talked about was that compound is a good base if the pK of its corresponding conjugate acid is more than 11. So, if the nucleophile employed here is such that the pK of its conjugate acid is less than 11, then it is a really good nucleophile. So, it would prefer doing SN2 reaction. Okay. And of course, it is important to use a polar aprotic solvent here because the reaction is already slow due to the steric hindrance. So, you want to aid it by giving the right kind of conditions. So, you want to use the polar aprotic solvent. In the case of secondary alkyl halides, remember E2 is also a possibility, but for E2 you are going to require a really good base, and for E2 especially you want the pK of the conjugate acid of the base to be above 11. Okay. If that is the case, then the compound will probably do an E2 kind of reaction. For the secondary alkyl halide, SN1 or E1 is also a possibility. You are forming a secondary carbocation, and those are considerably stable molecules, although not the best carbocations as we have seen, they can form, but again it is going to require some aiding. So, you will need polar protic solvents in this case, because in order to stabilize the carbocation formation, and also we will need nucleophiles that do not have a negative charge. Remember, when we want to form a carbocation, we are forming a molecule with a positive charge on it, and anytime we have a really strong base which has a good amount of negative charge on it, the carbocation is not stable enough. And so, for the SN1 kind of reaction to happen, we need nucleophiles that are weak and also the nucleophiles that do not have a strong negative charge. Okay. The only exception to that is nucleophiles like chloride, bromide, iodides, which have a negative charge but will not act as strong bases. Okay. Because of course, they are one of the most weak bases that you have seen, right. One of the things to remember here is whenever you form a secondary carbocation, there is a possibility of rearrangement. So, always be careful about the potential rearrangement that can happen whenever you form a secondary carbocation. So, let us go over the chart for secondary alkyl halides here. The first question to ask is the nucleophile or the base really strong? If the base is really strong, that is tertiary butoxide, again LDA, butyl lithium, these will only give E2 kind of product. So, they will undergo elimination via E2. Compounds which are not really basic but are strong bases like hydroxides, ethoxides, methoxides will do an elimination reaction, but remember they will also do some kind of substitution reaction. So, you will see a mix of substitution and elimination product. If that is not the case, and if you have a good nucleophile but a weak base, so a good nucleophile like cyanides, like thiolates, then you will see substitution product. And again with acetylide ions, this one that I have shown here, it is a really good nucleophile, but it is also a considerably good base. So, you will see a mixture of elimination and substitution products. So, SN2 or E2 can happen. Now, if you are dealing with really weak nucleophiles and in polar protic solvents like H2O, like methanol, like ethanol, and all of these cases you will see SN1 or E1 happening. Now, typically it is seen that elimination products are favored in the case of higher temperature conditions. So, E1 will predominate if the temperature conditions of the reactions are high enough. SN1 will predominate if at a lower temperature. Okay. So, that is the case for secondary alkyl halides. Now, let us look at compounds that are benzylic, allylic or tertiary alkyl halides. So, basically the kind of compounds that will form a very stable carbocation. Okay. These are also the compounds that have bulky substituents present on the carbon bearing leaving group. Okay. Now, whenever you are dealing with tertiary alkyl halides, since they form carbocations so effectively, one of the major pathways for them to react is SN1 and E1. Okay. SN2 pretty much does not happen because there is so much steric hindrance that SN2 on a tertiary alkyl halide is very rarely seen, almost not seen, right. So, it is not allowed, we can even say that. E2 will occur if we use really strong base like hydroxide, tertiary butoxide, ethoxide, methoxide, or even stronger bases like LDA, like butyl lithium. If we use compounds like these, then E2 type of reactions will happen. But again, the major pathway for tertiary alkyl halides is either SN1 or E1. Typically, SN1 and E1 both are favored in polar protic solvents. Okay. Typically, the compounds that will do this kind of reaction will be like alcohols, will be water, and also the compounds like chlorides, bromides, iodides, right. All of these will be performing SN1 type of reaction. So, SN1 and E1, since they involve the production of carbocation, again we do not want really strong bases to be present because the carbocation is not favored in that particular medium. Okay. Now, for tertiary alkyl halides, if we have to go over the chart, for tertiary alkyl halides, the question is the nucleophile or the base really strong? If yes, then it will do mainly elimination via E2 reaction. If not, if you have polar protic solvents like water, ethanol, methanol, ammonia, acetic acid, all of these compounds will prefer doing SN1 and E1, and which one amongst SN1 or E1 will predominate will depend on the temperature more often. And what we will see is at a higher temperature, we do see elimination being preferred over substitution. If that is not the case, then more often the only way the tertiary alkyl halides can react is SN1 kind of conditions. Okay. So, this kind of sums up our summary of substitution and elimination reactions. Now, the tutorial for this one is going to be a very important one because in that tutorial we will go over exact examples of which is the more preferred product, SN1, SN2, E1 or E2 depending on the given reactants. Okay. So, let us meet for the tutorial.